All right, good afternoon. Let me introduce the first speaker of this afternoon. I'm really pleased to welcome Michael Kaindl from BMW. I know Michael Kaindl since I started at Bosch and doing in-vehicle network. He was always present. He started his career in 1990, and since then he was always working on communication system for automotive. So he saw all major communication systems like Kaindl, FlexRay, and finally also he saw Ethernet. Today's responsibility is still on physical layer mainly, and high-speed communication technologies such as SerDes as well. And he's also contributing massively to consortia. So he was contributing to FlexRay consortium, I guess, and as well as to Open Alliance. He's currently active in TC9 and TC12. It's a really pleasure to have you here. Thanks.
Thank you. Thank you. I want to use this afternoon to start a short presentation and discussion about some gaps, and that's a nasty thing. And speaking about gaps in an audience which has created great specs, used several times, several million times, and that makes it not so easy, but I think it's worth to start this discussion and find some approaches to overcome potential gaps, introduce it for the next generation of the speed grades. When I speak about IEEE spec, I mean Ethernet in general, 802.3, different speed grades. And my examples are, one is the startup of an 100 and 1000 base T1 link, then something about MDIO issues, and one topic is about what's going on with shielded channels. The first example is startup under noise. Why it seems that the EMC was an underestimated problem there, and I will describe two setups which I used to do a first approach, and the next step to have an example of a more professional test setup, and as a summary, what is the result and what conclusion and what improvements we can make. The story started about 1.5 years ago when a first year came to me and say, hey, we experienced some problems with startup under noise. And say, oh, what are you doing? Yeah, we made an extended test and we used our EMC test equipment and tried to do startups there. And he described it as written in this box, hardly to read, and it's very easy. You apply a field, turn off the device, turn it on under the presence of field, look on the result, turn it off, and went to the next step. Question, was this a relevant test? We're not sure. Is it a test error? Also not sure. And is there something we have missed in the past? I go back and asking my colleagues from the EMC partners, FTZ, do we have an experience? I said, yes, we have discussed it in the early days, and we get the feedback from the PHY designer that it should be not a problem, because we have a different setup during startup, and we use a more robust signal, it should be not a topic. And we didn't see any errors, but have in mind that startup is a critical phase, the parameters are not learned, the channel is not compensated. I involved more a deeper investigation on it. But at the past, we have had no real feedback on impacts. Something I was aware that the test made by the first year exceed our current test setups, and it leads a long time to do it, because going down, going up, you need several seconds, you have to do a reset, you have to start up. Normally you step every 2 seconds from one step to another, and it's different, it takes a long time. And the other fact is that with the current setup and the current approach, we would not have seen it, because between each step in a normal test, the field disappears. If you have an error, the link has enough time to come up again. So I developed two setups. One is a very simple one, and I use a setup very similar to the IEEE receiver test, where we have a DOT using this challenging coupling circuitry, using generator with a balloon, and observe it with the PC. On the left, you see the real setup, not so much interesting. Checked that the spectrum is okay with the balloon and all that. I use an EMC tool. We can see it upstairs in the booth of Technica, where I can observe the MEC value. And during the test, I look what does noise have an impact on the link. I set up a link with a certain level of MEC, do either power on reset or a soft reset. Power on reset, turn it off hard, and a soft reset by communicating via the PC to the tool, say, establish a new link. In this simple setup, I saw some results. I used a sine sweep and a Gaussian noise. It has an impact on my startup behavior. And already in this very simple topic, I saw it is a difference whether I execute a hard reset or a soft reset. Some look at the tool itself. On the left, we see a value, the MSE test. We use an MSE value of 206, which was in the past of our criteria for qualifying the 100-base-1 tools and setups. And here we have established a link with 206. I do a reset. Do I come up? Look at the time, look at the level, and it works. The second topic was for the soft reset. It's the same tool, but in a different context. The tool allows to communicate, and we can test the link-up time. So you apply a soft reset, and you look at the link-up time. And what I've seen before, it was confirmed. But this setup is not the one as described from the first year. And it has so many side parameters. You'll have a lot of manual actions. Therefore, I use the second one. And here I use more closely to the EMC testing. I use the strip line and other methods like PCI and antenna measurements, and explain shortly on the strip line setup. I have my DOT, I have the strip line, I have a reset box which applies a 1 second power down, and put it into the chamber and observe it. I set up the EMC test tools to apply a field for 60 seconds and do a reset every 5 seconds. So you need some time to come up to do it again. And there's no sweep in between, and the field is always on. I use stripline up to 200 volt per meters, PCI with 160 microamp, and the antenna from 200 megahertz to 1 gigahertz up to 100 volt per meter. Same story about the observation. I look at the MEC value. You see normally you have something like 45 when it's going up, when you apply the field. One criteria is, do I see a big MEC value, or because it is a fixed 1 second power down, do a prolonged gap between the re-establishment of the link. It confirms the same. And still, first he proves that the report for the first year was correct, that he was not wrong. And what is the topic if you look for different vendors, if you look for different PHYs? I have 5 resets. It's not a statistical number. You need hundreds, for example, to do it. And therefore, I asked for an automotive test. And this brings me to the next topic. And also have to note, and it's not shown here, most of the failures or deviations we are seen in the out of band of the frequency. So normally with 100 base D1, your frequency goes down immediately at 60 megahertz, hardly to 100. Failures occur at the areas of 200, 300 megahertz. And if you want to go with this gap, the frequency range, it takes a long time. So I went to my partners, and have 2 of them. One was a setup one. I went to Ruitz to do the test for a gigabit circuitry with an automatic topic. And the second one was with the EMC topic for 100 base T1 with a DPI setup. And they confirmed the result. And here's in a very short form that we see there are failures. It's dependent on the vendor, and it's dependent on, it's different with different levels, so they're not the same. So It's a vendor-dependent behavior for startup under noise. I should add one topic. For setup one, Ruud made a very clever topic. They introduced a directional coupler. With the directional couplers, they can target the noise to only one of them. So you can select which one you want to target. The summary. For some application, it might be a critical topic if you have a delayed or a failed startup, because the software behind waits for the file to be ready to be able to communicate. And when we go back to the discussion of the morning before lunch, this might be also a topic for IEEE, because we go to in the low power mode, we have a different behavior in the sync mode, and once you have a field, it might be different to the one you have a stable and operation, or you have no field at all. And therefore, my request is that the startup has to be tested and independent from an established link. It should be defined as a topic also to have a robust startup. And as mentioned before, also for low power modes. For me, it seems that the test method with the AWG generator is more direct and faster than the one with CMC tools, much cheaper. And my request, we should work on this issue to get a definition and a test scenario for this. Second one, MDAO basics. When I speak about MDAO, I start with some basics. I will skip it because time is running. Why is MDAO important? Using MDAO for configuration. My experience with MDAO with 2 examples and a summary for improvement. Just to skip it, we have 2 different clauses. Most of you know and are aware, clause 22, clause 45 with clause 45 with extended data range, address ranges and some commands. The main topic is we have a 2-wire bus with open drain communication. We have I/O voltage 1.2 volt up to 5 volt for older devices. We have a variable of MDC frequency from a few kilohertz up to 2 to 10 megahertz, or even faster. And the MDAO is the interface for our configuration. So I skip the rest of the foil because it's known. Give you a view how we use the MDAO interface. And here for different 5 generations, what amount of data we bring into the devices. Starting with 100 base T1, it was a few kilobytes. When I speak about kilobytes, it's not the size of the data we bring, it's the size of the C files we found in the APIs given from the vendors for configuration. In reality, it's a few bytes in the early days, and up to 32 kilobyte for configuration of the hardware in the multi-gig. But it increased over the time, and it decreased over the functionality. We have, in the beginning, we have only pure hardware configuration. Now we have configuration for features, for the MACsec, for the PTP, and next time will be the IEEE features coming. So this, to summarize, the configuration is done via MDAO. The size increases over the speed grades, and there is no indication that there is a saturation of the increasing size. In preparation of this speech, I found also another use case where potentially we never experienced it so fast. MDAO might be the interface to access data we transfer via the OEM channel. So OEM might get also a communication way on a very slow and simple mode to communicate PHY to PHY. And also, MDAO is, in my opinion, then the mean of the access of this data. What is the consequence if you have wrong data communicated with MDAO? And there's 4 cases. That's always natural. One, there might be no function at all. Somebody says that might be the worst case. That it isn't, because you see it immediately. The case is B, C, D. Our daily business, and they're more severe, because sometimes you don't see that you have an error, or you see it only in a late state or under a certain condition. And it might be that you see it only in the field under a certain condition, and you have already passed all your tests. And I'll show it in an example on the next slide. But how can we get a deviation of the data we have written in? It might be by EMC or from internal noise. Currently, there is not reported that we have any errors, but this type of behavior I have seen in the past for a system-based chip of CAN and LIN, where you have suddenly a noise on the configuration file and you went in the state and you don't come back. We know from the feedback from the chip makers what a wrong configuration can do. And we get it always, oh, you have used the wrong configuration for your file, you don't get the results we have, you get a result which is not as good as we see, and you should use it. That's done with intended software, and we have no idea what happens if we get to such a state, if we have a peak on the signal during the configuration and what's going on. So, Josie, we cannot see immediately that we have a wrong MDA behavior, a wrong data written to the device and in the behavior, and we need some improvements there. The example, not really to deal with the failure, but it deals with also on weakness in the complete story. Look on timing. During the tests, we use the timing, make a reset, have introduced a variable as the device variable, as a tester variable, the time between executing the commands. Very simple, write the register, reset, wait the time, write the register, wait for the reaction. And we do it for the link-up time. And if you use a default time of 2 milliseconds, the link-up time is very, very long. And it goes to the link-up time, which we can achieve with a hardware reset if we wait for 60 milliseconds, 40 milliseconds. So that we find out why we potentially have observed before different link-up timings, and it depends from the timing parameter. Nowhere written that it's this case. And nobody can guarantee that you can have a variable link-up time or not have a variable link-up time in complex system. If you think of a Linux stack, and it might take 2 milliseconds, it might take 40 milliseconds. You get an undefined behavior by the software parameters. Then there was the idea, oh, let's check if you have written the correct data by reading it back. With this example, it's made on a normal file, it was a switch, it is shown, once you write the data and immediately read it back, there's no guarantee that you get the same value, because the internal processes might have changed the value already. And with this, you can only follow strictly the guidance of the chip maker to write data, hope that it's correct, and you have no guarantee that this configuration is really the one you wanted to write, it's received correctly, and the device behaves in the way you want to have it. Summary. The MDA gains some importance for us. It's used for the PHY operation, switch operation, and we need improvements of the data integrity, so we should introduce something like as I said before, check some bit error detection. We need an improvement on the definition of data handling in timing and structure. And it's important for us as we, via MDIO, do the configuration, we do the monitoring, we do the control of the device. And below a short list, we should establish a robust communication. We should have some means like checksums, check for correct data definition, check for the data consistency, timing. Next topic will be, we want to get more data out of the device, and it might be also good to have a high-speed access, also in low power mode. So MDIO is our view into the chip. And we should have test modes, adjustable IOs, because sometimes you need level shifters in between. And the list might be continued, and might be, just as I said before, it's a discussion, it might be a starting point for all the guys working with PHYs and switches to think about a good solution. It might be different to what I've written there. Another topic is I'm missing some parameters on shielded communication. Here I speak about EH, because at 1000-base-T1 we have shielded topics, and to do this, give you a short overview on base of the CH, then a view how we understand, most probably all of you understand the IEEE specifications, and I will change it to my view in terms of the EMC and some parameters on it. I've looked in the CH and found on the left side the different chapters with the parameters described. So it's just some bullet points, not a complete spec. So I found the most important topics in these chapters: 1497, 1498, 149C, where we speak about insertion loss, return loss, coupling, screening actuation, PSA, return loss. So there's a coding picture showing the effectiveness of all the topics on the channel, and I added this on the next foil with my view and how to understand it. IEEE make a definition of the protocol, make a definition of the TX behavior. It makes a definition of the link segment. The RX is left to the implementer. And one topic I hear my colleague or our colleague, Mehmet Tazibai, conformance to the standard is the key asset of IEEE. And I add the function before with the function I see also relevant for the working topic of an PHY. And according to the layers, slightly blue, the RX function, the link segment, which is comprising this big box, the RX function here, big link segment here. Then we have the protocol and the layer in these boxes in here, and we have interfaces to the higher layer. And when we remember, and here try to bring the view on this picture, what the IEEE describes so far, with symbolized with the blue sharped lightning symbol, we see the effect of the signal behavior, we see the impact of EMC on the signal behavior, on these topics, on the channel, on the MDIO. But there is more. And I added my view, and here I just marked the missing parts I'm missing. I'm missing that we have no idea about emission. What is emission? Because even if we have very low emission out of a shielded cable, we go potentially around the GPS antenna. So emission might be also a topic. And we have missing all interfaces which coming from the PHY. I'm not sure whether I present, but if I do measurement, I see sometimes these interfaces as well. I see the interfaces for the configuration, and I write down what I'm missing on the channel. Then one topic is I'm missing the mode conversion, because mode conversion covers both. It covers the signal integrity as well as the emission. And I'm missing some topics how I should apply a shield and what a shield might have an effect on the overall system, because it does not end it here. And as mentioned before, I'm missing effects on the complete other interfaces. The complete statement of IEEE is now in this topic, few sentences. It's electromagnetic capability. It's requirements according to standard EMC requirements. And with this, the implementers of the chips, the user of the chips, the end customer, and even our customer is left alone. And here's a summary on it. Mode conversion is not specified in the moment. And we should have a requirement on it. We should have it on the channel, on the link segment. We should have it at the MDI PCB level. I think that's, for me, a minimum topic, even if you use shielded cables, because I think it has an impact as well. And the short notice before, I think it's not sufficient. And I just can encourage to work on it, even if it seems that it's potentially at the moment out of scope of the IEEE, but we should work on it. We should have a generic concept how to introduce shielding and what is our understanding, what is a good way, because we are working on so many different solutions at the moment, including also the other interfaces. We have learned about configuration and control interface. This example of MDI, what might happen if you get a spike on the MDI interface and losing configuration data. We should also think about the other interfaces to the micro. And these are high-speed interfaces, like at the moment, the high-speed MI interfaces or PCI. They also generate noise, and they are also sensitive against EMC. And we should also think about ground and power supply, because when you think back to the presentation given about 2021, the shield concept does not eliminate by having a shield all other problems. So I think ground and power supply also might be a topic for getting the EMC problems tamed. And even if you say that we just look on the signal behavior, on the signal integrity, we should think that EMC is not an unidirectional topic. If you solve all topics, we also have solved the integrity stuff. And it's always the same. EMC has two sides of the coin, the emission and the signal integrity. With this, I close. There are gaps. And we have the chance, we as a group have the chance to close the gaps and work on it. And the other topic in my statement is, sometimes there is a real hard border between specification and between essential definitions and the implementation topics. This hard border, at least for me, in the automotive business, does not apply. Currently missing topics in finalization is done at the automotive, the Open Alliance, Open Alliance for Automotive Ethernet. And this is done when the chips are available and then doing changes. We have lost time, we have extra cost and potential. We have to change existing devices, existing architectures. So it's hardly done. It has a big risk that the non-conformant implementations escape to the market. As I said before, some topics are today out of the traditional scope, but we should work on having more guidelines on it. And some additional requirements will help to avoid these time-consuming pitfalls. A last word. Any topic we have not addressed might be a topic for having an interoperability issue at a late stage, with the consequence that non-standard products will go out there and establish a de facto substandard implementation, which would, the first moment we think it saves times and save cost, but in the end it will add extra cost and extra time. And one famous last word. We as automotive industry need you and the IEEE as a strong partner. We need it for the definition of the specifications and it's a strong standardization body. But the other side, as mentioned before with the EMC, the IEEE I think need also the automotive industry with the first tier suppliers, the OEMs, the second tier suppliers as their partners. With this, I close my presentation. Thank you for giving me the chance for this, some critical words. Thank you for the attention.
Thank you so much, Michael. I'm happy to see that you have again the appel to join IEEE and contribute. We cannot repeat more. It's really important that we show up there and do our stuff.
So
Steve, you have questions?
What I need to comment on is pretty much everything you're talking about is out of scope of IEEE and will never be in scope of IEEE, okay? We write interoperability specs for the data communications. If you have noise problems on your circuit board, that's your problem. We assume that you're good engineers and you can figure out how to solve that. We don't write tutorials telling you how to do something. We don't specify implementations. There's no power supply specs in there because we don't know what technology you're going to use. So I'm just saying that all of these things are written that way on purpose. The EMC specs really say, here's some possible things. EMC is your problem. Figure out how to solve it. Whether it's for automotive, satellites in space, data communications in a data center or whatever. So you're welcome to take a crack at writing guidelines somewhere else, but none of this is going to come back into an IEEE spec. Okay?
Okay. Any questions to Michael? Probably I repeat my question from the presentation before. So about the immunity of EMC on using IEEE. You have an opinion on that?
Yeah, I've mentioned it IEEE also here. I think it's always a critical state when you have to change the mode from a stable operation to a silent mode to a more low power consuming mode. The circuitry is changing, you change the state. And it might be critical for bringing some noise on it, then you have the big chance that you don't return to the state where you want to be. You might lose the synchronization. One bit might change things more easily than in a robust state, in an operational state, which turning on, do refresh, and have all the things working. This is one topic. And the other, that's for the impact of EMC. And the other topic is the low power mode itself. It has some regular meaning. With regular signals, we have seen some EMC emission topics. For example, the flex ray, where you see the FSS and potentially it does not come from the communication. Even we've learned it might be not a topic, it might come from the power supply.
All right. Any further question? Then thank you very much, Michael.
Okay, no problem.